Hello everyone, I hope you're doing well. I wanted to do another example of using variation of parameters. So let's consider the following second order non-homogeneous differential equation. And we can see fairly simply that the solution to the homogeneous is cosine 2x and sine 2x. Now to set up the variation of parameters, we create the problem y equals u1 times the first solution plus u2 times the second solution, and our goal is to find u1 and u2, both functions of x. What we do is we create a system of equations with u1 and u2 and their derivatives. So the first equation will be du1 dx times the cosine plus du2 dx times the sine equal to 0. The second equation, I will take the derivatives of my homogeneous solutions along with the du1 and du2. So negative 2 sine 2x, 2 cosine 2x, and all of this equal to tangent 2x. Now what we have is a system of two unknowns and two equations, but the unknowns are actually the derivatives of the u terms. So the most efficient way to solve this, of course, as we've seen, is using Cramer's rule, which we will do next. So the first determinant, which we generally will call w, will involve my solutions and then their derivatives. And when we evaluate this, we'll see we get 2 cos squared plus 2 sine squared, which is just 2. Then the w1, we replace this first column with these. And we get 0 minus sine 2x tangent 2x, which is sine times sine over cosine, which is the negative of 1 minus cosine over cosine, and upon reducing this as far as I can possibly go, this ends up being cosine 2x minus secant 2x, just using a little bit of trig. And then w2, I use those columns, and these guys again, but over here. So I get cosine times tangent, which is cosine times sine over cosine, so that yields just simply the sine of 2x. Okay? Now, with those, I'll go ahead and erase this. We find that du1 dx, which is w1 over w, is simply 1/2 times the cos 2x minus 1/2 secant 2x. So upon integrating, we find that u1 is 1/4 sine 2x minus 1/4 log secant 2x plus tan 2x plus c1. The c1 is critical. c1 cannot be 0. That would be impossible. You would never get a correct answer if you replace c1 with any value. That c1 has to be there for the remainder of the problem because that's where the homogeneous solution actually comes from. Then u2, which is w2 over w, is simply 1/2 times the sine of 2x, dw2, is this. Okay, and that gives us that u1, which is the antiderivative of this guy, will be negative 1/4 times the cosine of 2x plus c2. Now that I've got my apologies, u2. Now that I've got my u1 and my u2, I go back to the original statement of our proposed solution, and I just simply plug those in. Since our original statement was y equals u1 cos 2x plus u2 sine 2x, upon inserting these, I'll see that I get, this ends up being quite simply, c1 times the cosine of 2x plus c2 times the sine of 2x, because of the c1 term here and the c2 term here, minus 1/4 times the cosine of 2x times the natural log of the secant of 2x plus tan 2x. You get a whole bunch of canceling after you plug everything in. So this is our final solution. Now the question comes up as to how do you know when to use method of undetermined coefficients versus variation of parameters. So let's suppose we have a differential equation of the form where the a, b, and c are simply constants. And we're very specifically talking second order because that's the only type that I can use on variation of parameters. So it depends on what f of x is. So for the method of undetermined coefficients, I'll write it like this, the only f of x we can use are polynomials, exponential functions, sine, or cosine. So if f of x is any combination of polynomials, exponentials, sines, and cosines, and no matter how many there are, we would choose to use the method of undetermined coefficients. For any other possible f of x, we use variation of parameters. As it turns out, you can use variation of parameters for all of these cases as well. It's just overkill because it takes a bit longer. So hopefully that clears up a few things and gets you a little bit more ready.